I'm good. How are you?
Alhamdulillah, Alhamdulillah. Challenge. Let's start off. So today we'll talk about the growth factors. So tissue engineering and growth factors, uh, they go hand in hand, just like cells. Let's mute one of mute. Up सही है, clear. Thank you. सही है. Was a lot of background noise. Okay. Chalo, let's go ahead. Where are we? You can see the screen? Yeah? Okay, good. So yeah, so the what we are going to be discussing today will be growth factors and the scope of growth factors in tissue engineering and regenerative medicine. Malia, mute kar. I can't. There's a lot of background noise. Thank you very much. Thank you very much. So how can these growth factors be carried or delivered to the scaffold? What are the different ways? Materials for growth factors, strategies for growth factor delivery, and control growth factor delivery. So growth factors can be delivered in different ways. They can be a burst response, say, or they can be a very slow, steady response or sustained response. And what are the limitations of growth factors? Okay, that what our current understanding about growth factors is still very limited, though. So, what do you think? Why do we need growth factors? क्यों चाहिए? Why can't we do without growth factors? हाँ, I can't hear you. बहुत हल्की आवाज आ रही है.
Hello, am I audible?
हाँ हाँ अब आ रही है, आ रही है. I think what you should do is just come off. You're on two devices, so come off one device. I don't know. Maybe stay on the
Talking
other
with the
one.
headphones, I have logged out from the laptop and joined from the
हाँ
phone.
हाँ मोबाइल पे आ जाओ because that's more convenient for you too. सही है. So, but you can keep on muting and unmuting, so it's easier for us to actually maybe communicate. So, why do you think do we need growth factors? क्यों चाहिए? Can we do without growth factors?
Biomarkers or growth factors are the polypeptides and the proteins which are
हाँ, but
required by the cells to.
हाँ, yeah, but
हाँ,
why? Cells
but the
require.
cells help
हाँ,
key differentiation, proliferation,
yeah,
migration,
yeah. Just
and for
that,
their growth.
just for cellular. Can they affect bone? Can they affect soft tissue? Can they affect other Can they affect the mechanics? Can they affect mechanobiology or mechanotransduction? Can they affect the substrate that they are being carried on? Not just the cellular events. So growth factors have multiple dimensions and multiple roles to play. Okay, uh, they
Okay.
they are capable of triggering a variety of cellular process and multicellular morphogenesis during the development and tissue healing. So that is not just what they do. They kind of gives these signals to cells and tell them, listen, you need to do this, or you need to produce this enzyme or substrate. And then they kind of uh, are monitoring uh, and are kind of supporting the cellular functions at the same time. So the impact of various growth
Hello.
factors. I can hear you. I can hear you. So the impact of various growth factors on tissue regeneration may differ from one another depending on the enzyme and the binding proteins involved. So a protein needs two things to be binded onto a substance. And protein can be used on most of the growth factors are proteins. सही है ना? And this is a very common strategy. Okay. A lot of signaling molecules are used, not just platelet derived growth factor, insulin growth factor, fibroblast growth factor. So there are a number of growth factors which are involved in this, and all they do is to enhance the regeneration, enhance differentiation, as you mentioned earlier. Okay. And they can be anything. They can be anything. They're usually natural soluble proteins at regular cellular events. Uh, and they bind to certain specific transmembrane proteins. So they have certain specific preference to bind to certain areas. Okay. It is a little insight of what growth factor research can look like. Some papers that I have put up here. One of them is synergetic roles of TGF beta signaling in tissue engineering. So it was published in 2019 in the Journal of Cytokine by Quack et al. So you can see it has a significant role. One of the very interesting growth factors for periodontal tissue engineering is PDGF, or platelet-derived growth factor. This was published back in 2011 in the Archives of Oral Biology, and you can see the number of citations. If you go online and check out its citation, it has been cited a number of times because platelet-derived growth factor is such a critical growth factor for periodontal tissue engineering. Then again, in bioconjugate chemistry, strategies to control or mimic growth factor activity for bone, cartilage, and osteochondral tissue engineering. Another paper in cytotherapy, human dental pulp stem cells expressing transforming growth factor. So these stem cells are expressing transforming growth factor or transgene for cartilage tissue engineering. So they can have multiple effects. Okay, they can have change the morphology. They can be chemotactic. They can be metabolic. They can be apoptotic, or they can cause cell death, or and can be combination of these. Okay, yeah. So here we go. Like I said earlier, the growth factors, depends on they can have a chemotactic effect. So they can ask cells, hey, listen, chemically change these markers. Mitogenic effect, they can change the morphology of the cell or a cellular process. Apoptotic, or they can cause cellular death. Uh, Metabolic effects, so the cellular metabolism by mitochondria and other cellular organelles can be affected, or it can be a combination of these effects. So yeah.
Okay.
Now let's look at how these cells can direct delivery of growth. How can they be delivered uh, onto a scaffold? So there are three basic strategies. Number one is physical. Second is covalent, which sounds covalent means that there's definitely stronger bonding. And then the third is bioaffinity, which is growth factor immobilization, bioaffinity growth factor immobilization. What do you think in which one is the weakest and which one is the strongest strategy to be used in, say, any bone tissue engineering? Which one is the weakest?
Bioaffinity is the strong
Mm-hmm.
covalent.
Mm-hmm. And the weakest could be?
Weakest could be covalent, and bioaffinity immobilization is strongest.
Mm-hmm. I would say anything. Say so. Let me put a question up like this. Say you have a composite. You have seen dental composite.
Mm,
सही है.
yes,
Of
yes.
dental composite में
Yes.
I need to add hydroxyapatite. I have a powder. मैंने powder and hydroxyapatite dental composite में मिला दिया, and then I used it. That is one formulation. The other formulation is I've got BIS GMA, Tech DGMA, uh, inorganic fillers, मैंने वो ऐड किए, I add the growth factors and I add all the inorganic, organic, the colorants, the the initiators, the activators, and I made a composite. Which one of these composites will hold on to the growth factor longer? The first one or the second one?
The second one?
Clearly. So the first one is basically मैंने क्या किया? I've just physically mixed it together, like physical mixing.
Okay.
That's relatively weak. The second one, I'm chemically mixing these raw ingredients together. So physical is usually the weakest interaction because they're not chemically bonded with the molecule or with the substrate. They're just physically because I have put a paste together. I've put it inside the composite. They're just holding. If the material were to degrade, they would release out really quick. And this is a problem with the physical. And let's talk about what physical is actually. Okay. So physical encapsulation is you're encapsulating a growth factor, and then you're not using any chemical ionic bonding, covalent bonding, or bioaffinity. You're just physically putting taking growth factor and placing it. Okay. So one of the ways is that surface adsorption has been used. Surface adsorption is okay, I have a say for example I have a little disk. I have a disk here, and I'd immerse this disk inside a growth factor solution, and I take it out and I dry it. So the growth factor would have been eventually covered, would have eventually covered the entire uh,
Perfect.
surface, है ना? And
Yes.
whether more or less whether it has done chemical or physical, I don't know. But the first thing that comes to your mind is, well, it has covered the surface, then it's very likely to be physical. It's just staying on the surface, depending on whether the surface is hydrophilic, uski surface energy kya hai. And if I just, you know, if I leave it outside, maybe it washes away with the body fluids, or it's not very strong. So the growth factor gets absorbed onto the surface, so it can frequently result in inefficient retention of stable soluble protein and poorly controlled delivery. That is what happens with physical encapsulation. So poorly controlled delivery, and it's not very strong. Okay. Say, for example, you said, I want to release a growth factor immediately when I implant it in the body. Try physical encapsulation. Okay. And if you say, no, 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 I want to have a sustained release throughout a number of months, then you can go like, okay, now let's try with doing um, other technique. So yeah. So mix the growth factor with the polymer before gelation. So if you remember, I told you about mm, freeze gelation. Remember in the scaffold technique, है ना?
Mm, yes, yes.
Freeze gelation, freeze drying. You had a look at the videos that I shared with you.
TED Talk, yes.
टेड टॉक देखी थी?
Uh, yes.
गुड गुड गुड.
Last week, yes.
किसकी थी? एंथनी अटाला की, राइट?
All about kidney, yes.
प्रिंटिंग, किडनी 3D प्रिंटिंग, सही है. Okay. And were you able to access the videos of the lectures?
Not yet.
चलो.
Yes, no, आपने मुझे I think you have shared only the slides, not the recording.
Really?
It
Okay.
required permission. The recording required permission. I tried to
Ah,
open it.
ah.
And
Okay, then you could have just request if it requires permission.
I
Try
did.
t- if you are if when once we finish, do this. Once we
Mhm.
finish, uh, go on the videos that I've uploaded and see if you can access it now after we are done with this, and
Okay.
let me know one more time, okay?
Okay.
So mixing growth factors with polymer before gelation is one of the ways of encapsulation. Optimized properties of scaffolds are not affected. Bioactivity of growth factor can be retained. So growth factors have again they have a bioactivity a property. This is something which tells us that, okay, growth factor is able to perform its function or trigger these molecular events within a certain time limit to cause a certain effect and to tell cell, listen, you need to deposit bone, or you need to make osteopontin, osteonectin, rank, and you need to start depositing, osteoblasts, osteoclasts to deposit bone. So this is bioactivity. Another way of physical encapsulation is doing layer by layer assembly. Okay, bilayered or tetralayered coating. So what happens is, इसमें क्या होता है कि as I said earlier, imagine I have a disc, I immerse it in a growth factor medium, I take it out, I let it dry, and then I immerse it again. So the second
Mm-hmm.
layer would go onto the first layer. I take it
Yes.
out, I dry it, I coat it again. It's called as layer by layer. Okay. And it
Logical.
basically relies on electrostatic interactions, and electrostatic interactions are basically positive, negative, and they are relatively uh, weaker than covalent, but more stronger than just physical interaction. Okay, so there is some between oppositely charged polyelectrolytes and growth factors to deposit functional polymer coatings on surfaces of varying compositions and shape. So, depending on the substrate surface, any material you use, it has a charge on it. It can be positive charge, negative charge, and whenever we make nanoparticles, whenever we make any substrate, it is very important for us to find out certain things. Or when we talk about advanced characterizations, in our next course, उसके अंदर we will discover the role of pH, how pH can affect it, and we look at the physical properties that can affect uh, what we are talking about right now. So yeah, so
All
just
right.
keep in mind surface adoption, layer by layer self-assembly, they're all part of physical encapsulation. Then we are talking about the second thing comes up is covalent conjunctions. Covalent conjunction. So, as the name suggests, covalent is relatively stronger than physical. Okay. It is done to prevent initial burst of growth factors and prolong availability. So, growth factors somehow, when they end up in the body, they cannot hold themselves. They just release on their own immediately. And you have lost all the growth factor. Imagine you say that I need to have a growth factor that releases uh, the first day, the seventh day, and the 14th day. And then you can control the growth factor release. Okay. But over here, the problem with growth factors is if they are physically encapsulated, they will have an initial burst, but covalent can prolong the availability. It can improve the stability and persistence of growth factors, chemical enzymatic reactions between proteins and functionalized surfaces, and also helps us in harnessing amount, orientation, retention, and distribution. So, what are we talking about here? What we are discussing is how these growth factors, once they are covalently bonded, that means I'm chemically bonding the growth factor with the biomaterial that I am loading it on. I can load it inside a nanoparticle, inside a microparticle. I can load it inside a membrane. I can load it inside a gel. I can load it inside, say, the electrospun fibers.
Captain?
Okay. Scaffold. Yeah, exactly. And how much amount I am loading? Am I loading little amounts? Am I just loading the entire scaffold with growth factors? So a very important activity in covalent conjunction is a phenomena called as carbonamide coupling. And just this happens between the NH and CAA. So if you have a little understanding of chemistry, uh,
Mm.
any substrate or any chemical molecule can undergo chemical reaction if it has a functional group. Now, what are functional groups? Now, functional groups basically are these ends on a molecule that can release and bind with other molecule easily.
They have
So,
affinity bind with the other molecules, like they
yeah,
have negative charge.
yeah. So, any idea what functional groups can possibly look like, or what could they be?
look like means कि
नहीं मतलब what I mean to say is कि say for example you know what hydroxyapatite is है ना? You know hydroxyapatite?
yes,
Okay.
yes, yes, yes.
Do you know the formula of hydroxyapatite?
Not exactly, but उस पे hydroxyl group OH उस पे
Exactly.
change होगा.
That is the functional
That's
group.
the functional
OH
group.
group is
Yes.
the functional group. That is why it's called as hydroxyapatite. Now, hydroxyapatite can be changed to become fluoroapatite. Then you have changed the functional
If
group.
it is replaced by change in
Yeah,
functional group.
OH or
Right.
NH. NH can also be used. Okay.
And
So the
yes.
formula is actually Ca10PO46 OH twice. So calcium 10, the phosphate 6 molecules, and OH there twice. It's a very complex, like a honeycomb molecule. So OH is a functional group. OH can be changed. Similarly with bioglass, there are a lot of functional groups can be changed. Any molecule, OH, NH है, so it can interact, it can bond, it can form double bond, single bond with adjacent molecule. Next is something very innovative that has been happening very recently. Muscle-inspired bioconjugation techniques has been used. Now, why muscles I've mentioned here is the muscles are really fascinating. Uh, have you seen a muscle underwater?
No.
Muscles देख आपने muscles खाए हैं कभी? नहीं खाए. अच्छा, कोई बात नहीं. Let me see if I can show you what a muscle actually looks like. So these muscles are found underwater and they are attached to one another. Okay. And they're
Okay.
naturally secreting a polymer that even underwater they are attached. Now think of it in terms of dentistry. Now, in dentistry, we rely on bonding a lot of times. Imagine a bonding agent or a material that relies on the chemistry or is made up on the chemistry of muscles, polymer that we can use in an environment which is always around saliva or liquid and is always being challenged. So that would be really fascinating. And you can, if muscles can hold on to each other, one muscle can attach to another muscle and they can be found in bunches and you can pick them up and they're attached and they're so sticky. Okay. So Inca, they have a bioadhesive potential and it can be deposited on all organic and inorganic surfaces and covalent bonding through amino group and what happens in muscles is they actually undergo covalent inherently, so nature produces this polymer which now a very long time ago people or scientists they mimicked the polymer, they studied the polymer, okay, what are muscles making on their body, and they say, okay, can we make it in the lab? So they made a similar material in the lab that could have that can be used underwater. Okay.
Okay.
So that is one form of bonding as well. Then polymer brushes control polymer density all the way down to the nanometer size for better biological response. Polyacrylic acid brush is used here. So amongst these, carbamide coupling has been very popular, muscle inspired with polydopamine and polymer brushes. Again, there's a polymer brush which is put onto the scaffold and that has been used. Okay. Now let's talk about extracellular matrix inspired growth factor delivery system. Now we have talked about physical, covalent. Now we are on to
And
ECM inspired. Now we want something growth factors because extracellular matrix looks like this network of fibers. Okay, and it has a certain uh, architecture. If the growth factors deliver, the mechanism of the delivery of the growth factors can be in a way that the extracellular matrix can absorb it, can hold it. That will be really fascinating. So scientists have faced a lot of challenge initially in finding out, but what they came up with, they said that let's start with hierarchical structure-based binding biomimetic ECM nanostructure immobilization of bone morphogenic protein 2. So they said, okay, let's build up growth factors one after another in a hierarchical structure. Okay, layer by layer कर लें आप उसको, or just one on top of each other using their uh, um, charge potential. Um, and we know that BMP2 or BMPs, bone morphogenic proteins, are growth factor as well. So that was one mechanism. The other one, they have used adhesive protein binding mechanism. So now you can see that these are the growth factors and they have different binding. So one is red, blue. This is black, red, blue. Here you've got red, red, red. So they have got these sensors. Growth factors have got these sensors, and what they do is they only attach to the places where they feel like they have an agonist. Okay, so they can be an agonist, and they can be and the scaffold can have an antagonist, and they find and they detect. Okay, and they detect, okay, yeah, you are nice, I will come and bond to you.
Is it what you call scaffold immobilization? Is it the same thing?
Yes, 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 scaffold immobilization, yeah. So biomaterials decorated with heparin sulfate, mimetic molecules. This is actually immobilization means making sure that they are spread on top. Okay, this is a very highly spatiotemporal controlled manner. When I say spatiotemporal, that means the space and temporal organization is very, very sophisticated. You know, because we know that the extracellular matrix has a very dynamic microenvironment. It regulates multiple cellular processes. Also, it holds growth factors. It has the ability to bind multiple systems. Okay. And as I said earlier, multiple growth factors can be BMP, BMP2, VEGF, PDGF, FGF, transforming growth factors, IGF. Okay. And there can be a number of growth factors.
All right.
Okay. Now, biomaterials and strategies for delivery system. Let's dive into that. So let's start with the nanoparticles. Nanoparticle based strategy. So how can we entrap the growth factor inside? Can we decorate the growth factor outside? Can we coat it outside? Okay, is nanoparticle, microparticle? So synthetic polymer nanoparticles have been used, polysaccharide based. Have you heard this term before? Polysaccharides. Any material that is
Yes.
made up of polysaccharide. Polysaccharide का
I'm
कोई
not
material?
sutures. I'm not sure.
हाँ हाँ, guess कर लो.
Sutures.
Sutures, polysaccharides, or what else? What do you think?
I don't know.
Polysaccharides or glycosaminoglycans, GAGs, are present all around. They are these molecules, and one of the very common things that you can find polysaccharide is in the exoskeleton of a shrimp or crab. Okay, this is
Okay.
made up of material called chitin. And now
Titan.
chitin or chitin or chitin can be deacetylated to give us chitosan. Deacetylated mean उसके अंदर acetyl group होता है. We can remove the acetyl group and we can make it into a material called chitosan. And chitosan has been used in tissue engineering industry a lot. It is made up of glycosaminoglycan, polysaccharides, COC groups होते हैं उसके अंदर. So how do they act? How do they uh, these complex growth factor nanoparticles, how do they act? So signaling molecules bind to a target cell receptor and activate an intracellular signal transduction system. Now, earlier on, you were seeing this image of a growth factor which had these blue, red, uh, black legs. Okay. Now these have these specific, they target specific cell receptors, and then they trigger an intracellular signal transduction system. Now ये होता क्या है intracellular signal transduction system is the cells are so sophisticated that inside them there are a lot of mechanisms going on at the same time. And when these growth factors come in, they trigger more reactions, not just mitochondrial reactions or Golgi apparatus or the nucleus, DNA, and they respond. They're very responsive. So they, in terms, they're very smart. Okay, growth factor आएगा and tell cell, hey, listen, you need to divide, you need to multiply, or you need to produce, or the growth factor can also say you need to die in terms of cancer therapy. Cancer therapy, you need certain factors that we can kill the cells. Okay. Growth
Okay.
factors don't act in endocrine manner. They have low half-life and slow diffusion. That is one of the biggest drawback. Okay. Kind of you can say it's a clinical limitation when we think about devising using growth factors. क्या होता क्या है आपने growth factor डाल दिया scaffold में, by the time it reaches inside the body and it releases, it has probably lost its half-life. It's got a very low half-life. Once it releases, okay, you want to have, everything released in one go. Because if you hold it and and when if it is lost in translation, you will lose the properties of the growth factors. So this complexity of growth factors can be seen over here. Imagine let's factor A, factor B, and this is time, this is protein concentration. There was an initial burst, and boom, it went down. Initial burst and went down with time. But you can see the red line didn't go as fast as the green one, and they are actually representing these molecules. The red is this line, is this molecule, and the green is this molecule. So they are evenly spread. Okay. Inside the synthetic extracellular matrix, these growth factors are added. There was an initial burst release, growth factors got released, and it lost all growth factors and it came down to the baseline level. These ones, okay, which seem to be a little bit more dispersed, okay, they got released and they came down, but not as much as the as this molecule. No, 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 no. This complexity may vary. One growth factor can activate multiple receptors. Okay. Each growth factor can have a varying effect on different cell types as well. And again, external factor, ECM target cell location, growth factor concentration. So what I'm trying to say here is that these growth factors can act in various ways. They can trigger certain reactions. So one growth factor can target just one cellular function. That is why sometimes you need more than one growth factors. You require maybe BMPs. You can require PDGF at the same time or FGF. That is why you see papers when you start reading scientific literature, you will see that okay, uh, this just they're using multiple growth factors. Why do we need multiple growth factors? Each growth factor is targeting a specific certain response. सही है जी?
All right.
So we talked about clinical limitations earlier. A small subset of growth factors have gained commercial success. बहुत small, very limited amount. Not BMP has gone commercial. FDA has approved it. Bone morphogenic proteins have been used. Uh, in paleontology, they were starting to use a growth factor, which showed really in the clinical data was really interesting in terms of the clinical attachment level gain, bleeding on probing, and bone loss. So, so
Which one is that?
I think it is PDGF. PDGF.
Yeah. Okay.
Yeah, try to read the paper when you get time on the one that I
Yeah.
showed you. It was published by a Buckeye graduate, um, Dr. Fawad Javed, and he did his PhD from Karolinska, and he published it, and it has gained a lot of citations since then. A
Okay.
short effective half-life, low protein stability, and rapid deactivation. These are the problems. Okay. Another problem that is not mentioned here is the cost. They are really expensive. Okay. The cost effectiveness is an issue. Sometimes the growth factors, because they are being extracted from something else, and they cost, their production cost builds up. How are they extracted? That affects how you can, acquire them. So FGF1 is intrinsically low stability half-life of 1 hour in serum at 37 degrees centigrade. So if you plan on using fibroblast growth factor, do remember that it has low stability. Okay, the half-life is of around 1 hour in serum. That means wherever you want it to function within the first hour or an hour and a half, it will do its job, and that should be done. Then comes beta FGF, which is a divergent from FGF1. It has a half-life of 3 minutes, which is really short. So that means that I use a very high dose of growth factors, because within 3 minutes, whether it was once I put a scaffold with growth factor inside the body and I want it to reach, say, I'm putting it inside the jaw and I want it to go in the entire mandible and, affect all the cellular functions there. 3 minutes is not enough. So you need a higher amount or quantity of it. VEGF, or vascular endothelial growth factor, which is used in a lot of studies with specifically on endodontic tissue engineering or endodontic regeneration. It has a half-life of 50 minutes after IV administration. So lack of cost-effective methods to produce recombinant growth factors at supraphysiological levels. That means there are normal physiological levels, there are sub-physiological levels, and there are supraphysiological levels. So it makes you think, why can't we just put supraphysiological levels in a scaffold and put it inside the body? And by the time it reaches, it will be at the normal physiological level that the growth factor needs to be used at. So there have been studies as to who are in the past, and what they've done is they've used a very high dose initially. So by the time the growth factor travels on to its target destination, it has reached its point, and it can act wherever it has to do, whatever it has to do in that area, whether it's VEGF, FGF, PDGF. So yeah.
Okay.
Let's talk about the growth factors targeting bones specifically. Now, this table has been taken by Robert Lanza's book, and I don't know if I shared it with you. I can do that. Have I shared the book with you?
Um,
No.
in first presentation, there were,
Uh,
number of books that you introduced, like three or four.
okay. So now the growth factors that we can think from the top of our head are BMP2, FGF1 to 18, and insulin growth factors. PDGF are two different variants. They are AA and BB, PTH, transforming growth factor beta, VEGF. Okay. Now, where are they being studied? Okay. BMP specifically for bone, cartilage, FGF for bone, muscle, blood, uh, and blood vessels, IGF for bone, cartilage, muscles, PDGF, bone, cartilage, blood vessels, muscles. So a lot of these, you can see the common pattern you can see is bone, cartilage, or
Bone.
muscle. Bone is very common. What were the
Yes.
observed functions? What did they actually do when they were in there? Okay. So BMPs cause differentiation and migration of osteoblasts with accelerated bone healing observed. That's specifically a targeted bone. It's a bone morphogenic protein. It has to target osteoblasts. FGF, fibroblast growth factor, it affects the migration, proliferation, and survival of endothelial cells, increase osteogenic differentiations of MSCs. MSC stands for mesenchymal stem cells. Okay. So when you can differentiate mesenchymal stem cells, when I say osteogenic differentiation, that means the stem cells are differentiating to become osteoblasts. So yeah.
Two glasses.
Have you seen
Yes.
stem cells? Kabhi dekhe?
No. In
Okay.
Ziauddin, I did master from Ziauddin, so
Mm-hmm.
there was a lab. Different
Mm-hmm.
students used to work, but I never got a chance to go inside and
Cool.
see.
उनके पास थे स्टेम सेल्स थे उनके पास?
Yes, they used to culture the cells there. Different students were working on that.
हाँ, देखो culturing cells is very interesting, but whenever you go in a lab, find out what cell line it is. Is it primary cell line? Is it secondary cell line? Are they stem cells? Because if someone is using stem cells, then the value increases. Why? Because stem cells can be differentiated. You can use different फाइब्रोब्लास्ट यूज हो सकते हैं, केराटिनोसाइट्स यूज हो सकते हैं, एंडोथेलियल सेल्स यूज हो सकते हैं, they have already been differentiation. Bone cells use हो सकते हैं, osteoblasts use हो सकते हैं. But when somebody says I'm working on stem cells, that becomes more interesting and exciting. क्यों भाई? इसलिए क्योंकि stem cells को we can trigger. Okay, now you produce os you know you can undergo osteogenic differentiation. Show me bone markers. The stem cells will start showing bone markers. Okay, now you make fibroblasts. You convert stem cells into fibroblasts. So you can change. Okay, you can because they can differentiate. Okay,
Okay.
multipotent or tutipotent नाम सुना है कभी? Multipotency, tutipotency,
Yes.
tutipotent cells.
I think it's based on their potential to differentiate on different kind of
Yeah,
cells.
yeah, yeah. So if you remember, if you go back, this is actually very, very early when we talk about fertilization, when we talk about bilaminar disc and trilaminar disc and epiblast and hypoblast and endoderm, ectoderm, mesoderm. So uske andar usually there's a phase when the cells are moving. Initially they are multipotent, but they lose their multipotency and then they become totipotent. Multipotent is they can differentiate into any cell type of the body. Okay. Coming back, IGF are specifically proliferation differentiation of osteoprogenitor cells. PDGF is targeting osteoblast replication, type 1 collagen synthesis. Now, that is interesting. Now, we know that growth factors can affect collagen, calcium synthesis, alkaline phosphatase activity, uh, whether they're producing affecting the DNA of the cell. So growth factors have the potential to go all the way to the DNA and alter it as well. Uh, PTH targeting bone, TGF targeting proliferation differentiation of bone forming cells, enhances cartilage formation and anti-proliferative to epithelial cells, and then VEGF specifically for vascular vasculogenesis and very interesting angiogenesis. So a lot of papers you will come off when they're talking about dentine pulp complex regeneration or endodontic tissue engineering. You will always hear VEGF being used, VEGF, because VEGF or vascular endothelial growth factors have been shown to produce or trigger angiogenesis. Okay.
Okay.
Now let's talk about delivery strategies. Okay. We talked up initially on physical, chemical, and ECM inspired, bio-inspired, or immobilization. Now there's certain other things also that can be used, and there are certain specific delivery strategy uh, that is adapted for these certain molecules. Now, let's talk about these molecules: nucleic acid, small molecules, bisphosphonate, growth factors, endocrine, and inorganic biomaterials. Now, each of these can usually adapt a certain strategy which will definitely work. Okay. So, say for example, if you are targeting using nucleic acids, miRNA or siRNA, जिसमें COVID vaccine बनी है, सही है? You can go for an intracellular or intranuclear pre-programming. The COVID vaccine came in, and you know that some vaccines were made or RNA, some were based on DNA. Uh, and if you come across the people who made it, you will hear the name of Robert Lanza as well in them. Small molecules, example, bisphosphonates. We know bisphosphonates induced has been is a very interesting topic in terms of jawbone and its effects of the bisphosphonate uh, uh, ingestion in the body has an effect on the bone. The delivery strategies that have been adapted specifically for these small molecules are surface absorption and sustained release. So, growth factors we have talked about, surface presentation and control release. That is something that you want to do. If you're talking about endocrine activity in which vitamin D3 or parathyroid hormone, so you really want a time controlled release in these. And if they're talking about inorganic biomaterials, which of the inorganic biomaterials, can you think of any inorganic biomaterial? Inorganic, organic और
Mhm.
inorganic में तो difference पता है, right?
Right.
Right. What is
No
that?
idea about the CH group होता है उसमें inorganic compounds
Mm-hmm.
covalently bonded and
Mm-hmm. टूथ में ऑर्गेनिक कंपोनेंट क्या है डेंटिन में?
dentin में
डेंटिन का इनऑर्गेनिक ऑर्गेनिक कंपोजिशन क्या
hydroxyapatite is inorganic.
है? करेक्ट. ऑर्गेनिक कंपोनेंट इज कितना
Organic
परसेंटेज?
is
4%
uh,
collagen. Okay, it's water
collagen.
based, right?
Okay.
It's collagen
Yes.
molecule. So
Yeah.
that's the water component in there. Inorganic. So
Yes.
inorganic biomaterials में आपके all calcium phosphates, apatites, bioglass. Have you heard about bioglass?
No.
Okay, we'll talk about that. So usually the delivery strategies within organic biomaterials are surface absorptions and depositions. That is why uh, we have so this slide specifically was targeting on certain specific biomolecules and the delivery strategy that are adapted for those specific biomolecules. Okay.
Okay.
We talked about these strategies. We talked about physical, chemical, ECM inspired uh, modification. Uh, think this is just repetition. I did engineering growth factors, stability enhancements, improve stability. Let's move here. Physical encapsulation. Yeah, I think we've talked about the three approaches. This is just a repetition. A physical encapsulation, mixing a growth factor in a polymer, convenient to synthesize. So if you physically mix it, it's easier to make it, but your growth factors are not effective. Disadvantage is that is low loading activity. Or you cannot load
Yes.
too much. There's a certain concentration, but there should be a balance. Okay. Say, for example, you said, I have my polymer 80% and 20% of its growth factor. If you do a 50-50, you know, then the polymer, because polymer is just like a carrier. You want the carrier
Vehicle.
to
Yeah.
stay inside. Once it's undergoing degradation, only then it releases the growth factor. Okay. Absorption, adsorption. Do you know the difference between absorption and adsorption?
Uh, Adsorption is on the surface of a material,
Hmm.
and absorption is inside, like deep within the material.
I think it's the is it the other way around?
Adsorption
There's more
with
bulk.
D is on the
Yeah,
surface.
adsorption on the surface. Okay.
Yes.
Okay.
And
I thought
absorption within the material.
absorption is on the so adsorption is on the bulk and adsorption on the surface.
No, opposite.
Opposite. Yes, yes, yes. Absorption is on the surface and adsorption is on the as I say, I've said here, adsorption on the surface of the scaffold release, and absorption on the bulk. I think let's double check that. You make a note of it. Let me make a note of it. Just double check that.
Mhm.
I think absorption is more on the surface than adsorption. Look it up and let's discuss it next time we meet up, huh?
Okay.
Adsorption and adsorption. Now, we talked about some limitations earlier. High-level proteolytic activity in vivo leads to poor growth factor stability and short half-life, 3 to 50 minutes for VEGF and beta FGF. High cost and adverse event. Now, these growth factors are really expensive to acquire, to play around with in lab, but in order to do the research and to find out how they can be used, we need them. What are the side effects? And poor effectiveness are mainly linked to suboptimal delivery systems and lack of control over growth factor signaling. So, uh, in order to overcome this, well, the 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 disadvantage is still there. There's suboptimal delivery because some growth factors they are released immediately and the intensity goes down. There are ways and mechanisms to make sure to stabilize them. Say, for example, you entrapped a growth factor inside a molecule, a microparticle or
Mm,
a nanoparticle. Another way to
nanoparticle.
do it is कि you have decorated a growth factor on top of the microparticle. Say, for example, आपने microparticle बनाया and then you say, okay, I'm just going to coat the microparticle with the growth factor. That is one way. The other way is, hey, I made a microparticle or nanoparticle and I'm entrapping it inside the particle. The particle has to burst open and only then the growth factor is released. सही है. Have you
Okay.
heard of self-healing dental composites? Self-healing
Self-healing dental.
हाँ सुना है आपने? क्लिनिकल ट्रायल्स हो रहे हैं सेल्फ हीलिंग डेंटल कंपोजिट्स के.
No.
क्लिनिकल ट्रायल्स हो रहे हैं इन किंग्स कॉलेज एंड इन द यूएस. सेल्फ-हीलिंग dental composites ऐसे होते हैं, they have microparticles. Inside the microparticles there's a monomer. Whenever the fracture reaches the microparticle bursts and releases the monomer, and the monomer seals the crack, and it then seals the fracture. Okay, and these micro
Okay.
nanoparticles are made by I think polyurea formaldehyde or polyurethane based materials से बनते हैं. But these are, imagine having a composite placed in you and then never using it, never replacing it.
Mm,
Bas once it's done. Yeah. Now you have heard of self-healing
yes.
composites, and you can ask around people that
Not
who
perfect.
नहीं लेकिन बहुत है. There's a lot of work going on self-healing composites. Uh, so the solution to this, to solution to having the side effects of suboptimal delivery and lack of control is to use something called as advanced drug delivery mechanisms. Now, what are those advanced drug delivery mechanisms? Okay. They can, as I said earlier, they were gels, they are microparticles, they are nanoparticles. Well, those are the advanced drug delivery systems. Now,
Okay.
I have a chart here which I've adapted, and it's showing you different products. It is also showing you the approved authority that have approved those growth factors. Okay. So, say for example, these are commercially available products. So, yeah, and they're used clinically. One of them is augment bone graft. It has PDGF growth factor. The delivery system is beta tricalcium phosphate or beta TCP. It is used in ankle fusion or hindfoot, and it is approved by the FDA. So it is being clinically used. Same goes with this material. This material, Regen D, has got EGF. It's a cellulose gel. It is used for foot ulcer. Okay, it has been approved by the Ministry of Food and Drug Safety in South Korea. Then Regenerix or Citrix, sodium carboxymethyl cellulose based topical gel for chronic diabetic wound, approved by FDA in 2018. So as you can see over here, a lot of commercially approved products are available. but you don't see much happening in the dental world. Okay. Although
Okay.
the latest year that you can see is 2019. That's almost 7 years ago. Okay. So so maybe there are new products that have come in, but these are the ones that are clinically used. And look at how many different growth factors are used and the delivery vehicles. This is a collagen sponge. This is a cellulose gel. This is a collagen sponge. This is an IV injection of the growth factor. Again, a collagen. This is a subcutaneous injection of the growth factor. Okay. And this is a beta tracker. This is an inorganic compound. Inorganic. Okay. Now, let's talk about inorganic materials. Now, what we know of inorganic materials are that hydroxyapatite is inorganic, tricalcium phosphate is our inorganic, alpha TCP, beta TCP, octa TC, calcium phosphate. These are all bioceramics. Okay. They can be used as a growth factor as well, not just biological growth factors or that are available that we talked about. Now, these bioceramics can also be used as growth factors. Okay. Q, because they can trigger bone healing. Now, there's something called as bioglass I've written here. You haven't heard. Have you heard of bioglass? सुना है आपने?
Never. No.
No. Have you heard of Sensodyne?
Yes.
Have you seen their toothpaste which says enamel repair and protect?
Yes.
ऐड तो बहुत आते हैं उसके. उसका एक है
जी.
वेरिएंट, उसका नाम है enamel repair and protect. If you ever get a chance to go to any store which has Sensodyne on the shelf, go there,
Hmm.
turn it around, look at the ingredients, and read. That product has got bioglass inside it, but it comes with the name of
Okay.
Novomin. Now, what bioglass is, and I think in the next few slides we'll talk about this. And there's a long story about bioglass. As the name says, it's biological glass. It's actually called as bone bond. So it was used in the World War II to bond the bones of the soldiers which were fighting in Vietnam. Okay, so the scientist who
Okay.
made it, his name is Larry Hench. Uh, and I had a chance to meet him just one time. He passed away 5, 6 years ago. I think maybe more. But he was the person who made it in his lab, and he sent the product to uh, Vietnam. And then the doctors called him and told him, "What have you done?" He said, "Okay, I just made this chemical which is made up of silica, 45% silica. That is why it is called as 45S5." Okay. It's got different
Okay.
ingredients, different formulations होती हैं, but majority now bioglass has been used in different ways. इसमें भी एक functional group है. That functional group has been changed. Strontium होता है. Substituted bioglass मिलेगा आपको. Fluoridated bioglass मिलेगा. You'll see those papers in and with GIC incorporated fluoridated bioglass or composites. Strontium substituted, niobium substituted, magnesium substituted, iron or silver substituted. तो different तरह का होता है. And what image I've shown you here is sort of a porous material. Now, what is the drawback of any ceramic material?
I think ये बायोडिग्रेडेबल नहीं होंगे.
Uh, let's think of it in mechanical ways. Mechanically, क्या होंगे? Ceramic का क्या drawback है? Ceramic तो आपको पता है, आपने ceramic पढ़ा होगा.
Yes.
हम्म, क्या मटेरियल है? क्या प्रॉब्लम हो सकती है मैकेनिकली? You know the concept of compression, tear, tension, shear,
Yes. Yes.
है ना?
हाँ. ब्रिटल होगा सेरेमिक.
Exactly. These materials are brittle. They are tough. Okay. But They are
Yes.
brittle. They are, okay, they can crack. So yeah, that is
Yes.
their drawback. Okay. Now this is
Mm.
a person who invented bioglass. Okay, his name is Larry Hench. And the story I already told you, he Vietnam War में बनाया था, and it is made up of 46.1 mole percent of silica, sodium oxide, calcium oxide, uh, termed as 45S5. Now there are different formulations. 65S5 भी है, 51S5 भी है, and there are different ones. But for Bioglass 45S5 is the main formulation. It's actually available in a lot of things around you as well. So Sensodyne, it is used as a dentine desensitizer. Okay, it has been used and it has been added, and it can then go into the dentinal tubules and prevent and protect anything to go inside the tubules and trigger sensitivity. So yeah. भाई बनता किस तरीके से है? It is made by a process called as sol gel versus melt quenching. There are different ways. Sol gel is the most convenient way to make bioglass. Moreover, the bioactivity in melt drive silicate glasses is possible only in limited compositional range. So the process is convenient in the lab. It's very easy to make in the lab. And one of my PhD students has is working on making a bioglass. And this is me in the conference in Liverpool, and I met him, and he was signing a book. He was writing a book, and Larry Hench. That was a long, long time ago. Now let's talk about tricalcium phosphate. Okay, we talked about bioglass, which is a has been used so many different applications, used as a growth factor. Let's talk about tricalcium phosphate as well. Now TCP is also a calcium phosphate. It has been used in tissue engineering as a growth factor for triggering bone regeneration. Now, the TCP comes in two different types. There's alpha TCP and beta TCP. Okay, so the beta TCP जो होता है is the component of several commercial mono, biphasic, bioceramics, and composite. Now, beta TCP has been used. Uh, I think I've written down the molar ratio of calcium to phosphate is 1.5. Do you know the molar ratio of hydroxyapatite molecule?
अच्छा एलोप्रीन कहाँ जा रहे? I'm sorry, no idea.
The molar ratio of the calcium phosphate of hydroxyapatite is 1.67. Okay, that means the moles of calcium to phosphate in. So if you're making hydroxyapatite inside a lab and you want to check the molar ratio, uska calcium to phosphate ratio will be 1.67. This one has a little lower calcium to phosphate molar ratios around 1.55. So it comes in alpha and beta. Uh, the reason alpha and beta have also been used and adapted is because one of them has a degradation which is very fast. So if you want within weeks, you can use that. Beta TCP is used mainly for preparing biodegradable bioceramic shaped as dense in macroporous granules and blocks. Alpha TCP is a major component of various hydraulic bone cements. Okay, it is used mainly as fine powder in preparation of calcium phosphate cements. So a lot of times you will see alpha and beta TCP in different variations. Anything which is made up of calcium phosphates will either have a variant of tricalcium phosphate, tricalcium phosphate. Now we've talked about growth factors. बात कर ली हमने we touched up upon the uh, um, bioceramics. What type of bioceramics? Talked about very little about bioglass क्या होता है. Little bit about alpha TCP and beta TCP. Now we're talking about drugs. Now drugs can also be used as growth factors. Okay. And nanoparticles have are one of the ways that these drugs can be used as, and they have been used as a carrier. Triclosan loaded nanoparticle prepared from poly-DL lactide chlorglycolide or poly-DL lactide. Okay, Now, I've shown a picture over here of a paper of a review in the journal. This was published in the Journal of Advanced Sciences. Drug delivery nanoplatforms for oral and dental application, tissue regeneration, infection control, and cancer management. Very interesting paper. If you get some time, have a look at it. It has shown different ways of how drug delivery nanoplatforms have been used for oral and dental applications. Now the image shown on the top right is showing you, different things. There's something called as dendrimers, metal core shell, liposome, nanofilms, nanofibers, micelles, polymer micelles, polymer particles in silica. All these, all these agents have been used to entrap a drug, if not entrap, but coat it outside. That is one way to do it. Okay, and their
Okay.
chemistries govern how they use it. Now, the chemistry is really, really fascinating in these. And as a tissue engineer, if you want to be a tissue engineer, you need to work with biologists, you need to work with a chemist, you need to work with a physicist, you need to work with a mechanical engineer. You're sort of all in one. Okay. Amongst all
Yes.
this is a very interesting molecule. इस molecule का नाम है tide glucid. Have you heard this term before? Tide glucid सुना है कभी?
No.
Now, tide glucid is an FDA approved drug for Alzheimer's. Alzheimer's तो सुना है ना?
Yes.
So ये dementia, Alzheimer's. Okay. So tideglusib has been used. Now, what is fascinating about tideglusib is that tideglusib has an effect on dentine regeneration. Now, this is the last slide. There have been a lot of studies, and these are relatively recently. As you can see, I've put up 2, 3 papers here. Okay. One is saying evaluating the effect of tideglusib loaded bioactive glass nanoparticles. Now आपको पता है कि tideglusib क्या है, bioactive glass क्या है, as a potential dentine regenerative material. This one is published in Scientific Reports, which is a Nature journal. Promotion of natural tooth repair by small molecule GSK3 antagonist. And this was published in Journal of Dental Research, which is the top journal in dentistry, JDR. Translation approach for dentine regeneration using JSK3 antagonist. सही है. So what it does is this molecule triggers the dentine regeneration. There are a lot of studies on it, and you can go into detail how this molecule triggers the odontoblast to deposit more reparative dentine, secondary dentine, primary dentine, or mantle dentine. How does it do that? But can equally enhance reparative dentine formation to fully repair an area of dentine damage up to 10 times larger, mimicking the size of small lesions in humans. Now, this is very interesting for us as a dentist. This is a fascinating molecule. Why? Because it's already being approved by FDA. And we, in our clinical world, are using it at maybe nanomolar or micromolar levels, and it has an effect. Okay. Now,
Okay.
this concludes our growth factor presentation today because हम लोगों ने बात की है on uh, drugs. We talked about inorganic growth factors. We talked about what types of growth factors are used where, how are they entrapped, how are they delivered, what are the limitations of it. So yeah, कोई questions है? Do you have any questions?
No.
Okay. I will